Hey, this is Warren Redlick. Drew Baglino, pictured over here, is one of the top people at Tesla. Drew, Zach Kirkhorn, and Elon Musk are the three key people, according to the Tesla website. If you ask me, Drew is the backup CEO. If something were to happen to Elon, Drew would be the next CEO. This is an event at Stanford University. It was about energy storage. Drew spoke at length. He covered a lot of topics. He talked about Tesla scaling. He talked about battery swap, solar roof. He talked about mining and refining. He talked about battery life. He talked about recycling battery materials, cathodes, regulatory structure, peak oil, and so much more, supply chain. One of the biggest takeaways for me from this event was how impressive Drew Baglino is. I believe I am the leading member of the Drew Baglino fan club. I'm president of the Drew Baglino fan club. I think this guy is brilliant. I think what you get from this is his depth of knowledge and his breadth of knowledge. He knows a lot about a lot of different things related to Tesla and things even outside of Tesla, but that are relevant to Tesla. And this is something you see in the Tesla leadership team. I've talked to other people in the Tesla leadership team. They always have broad knowledge. They always have deep knowledge. These guys work really hard and they learn a lot and they know a lot. Very, very impressive. Same thing at SpaceX with Gwynne Shotwell, by the way. Same thing with Siobhan Zillis at Neuralink. You see this across Elon's companies. He recruits great people and he puts them in positions where they are able to learn a lot about the business themselves. They know the breadth of the company. They know the depth of the company. You're going to see a lot of that here. But the biggest thing that they talked about here was how Tesla is going to scale manufacturing and how the world needs to scale manufacturing of batteries in particular in order to enable electrification and shift society to the transition to sustainable transportation and sustainable energy. So let's get into it. Here's the first clip of Drew talking about scaling.
To build about ranging from a few hundred, let's take it 300 to 500 terawatt hour batteries to power the car, if you use that for electrical grid, certain duration of storage. So what's your thought on the scaling issue?
We are at that point where the exponential growth curve becomes really painful. You know, when you're talking about something that you make 5 of, making 10 of it the next year, that's easy. And then maybe 20 of it the next year is also easy. But when you're going from, you know, making millions, like Tesla did 1 million last year, to 2 million, and everybody in the industry is trying to double in that way, it does really become a scale problem. If we stay on pace, which we're currently at, like as an industry of growing 50% year on year, it does seem possible that within 20 years, the 300 to 500 terawatt hours of batteries will be built. It's kind of nutty. It means we need to get the global annual, you know, production capacity of batteries to like between 15 and 20 terawatt hours a year, which is crazy. We're barely at a gigawatt hour now, and at a gigawatt hour, there's a lot of like inflated numbers versus what was actually produced.
Just to be clear there, he said we're not at a gigawatt hour yet. I think he meant terawatt hour. We're producing a lot more than 1 gigawatt hour of batteries worldwide. Tesla alone is producing a lot more than 1 gigawatt hour of batteries. I think he meant terawatt hour there and he misspoke. I just wanted to clarify that we're trying to get to 15 to 20 terawatt hours a year, and currently, so to get to 300 to 500 terawatt hours total, globally the world is producing more than 1 gigawatt hour, but nowhere near 1 terawatt hour. I don't think we're close to 1 terawatt hour of battery production, but we're way over a gigawatt hour.
It's massive growth, and the difference between, like, I don't know, growing iPhones by 50% a year and a car battery or grid storage at 50% a year should be obvious to all of you. Like, there's a lot more mass in a car than in a phone, and that mass has to come from somewhere. So ultimately, that mass, largely the cathode, largely our highly refined transition metal, needs to come out of the ground, and with the like ore ratios that exist of, you know, 100 to 1 or 50 to 1 if you're lucky. Maybe you can get 20 to 1 depending on the resource. If you go to manganese, maybe you can get 10 to 1 or 5 to 1. It's still a lot of earth that needs to be moved at least once to get that 300 to 500 terawatt hours out of the ground.
So that's a big challenge, getting the material out of the ground. There was an interesting thing in there about ore ratios. So I'm not sure I completely understand what he means by ore ratio, but what I think he means is the amount of earth you have to move to get a certain amount of the mineral you're trying to get. And so with nickel, it's a much higher number than it is with manganese. That may be one reason why Tesla has been talking about using a primarily manganese-based cathode, because it may be easier to get large amounts of manganese. And if you can make a decent cathode with manganese as your main as your main cathode material, that might make sense. Really not completely clear what he was going for there. I don't think we got an answer to what he meant by ore ratios in this video. So maybe we'll find out more about that. Maybe I'll be able to find out more by asking some other people. But right now, I don't know. I just thought that was an interesting detail. Next, Drew gets into this really interesting idea about how the supply chain for batteries exists today and how it needs to change in the future. Listen to this and I'll explain a little bit more.
For a while, the battery industry could scale within the constraints of the entire economy that exists of materials and of refining and of chemical production and everything. But we're not really there anymore. We need to invest in our own everything, which is an opportune time when you're investing in your own everything to reevaluate what you're investing in. To date, the battery industry has been on the coattails of everybody else. So nothing has been like deliberately built for it. Full supply chain, that is true. You know, like the electrolyte is being built at some oil refinery that's doing a whole bunch of other petrochemicals, and like the electrolyte is a side business, and honestly, it's kind of annoying. You know, the graphite historically also has been coming out of some petrochemical process, or maybe some coal mine kind of thing, but has again been sort of a secondary thing that they could make some money on.
This is an important detail here that I was not aware of before, that the supply chain for batteries consists in a lot of materials, and there's some other industry going on, and they happen to make this part of the battery supply chain almost like as an accident. It's not something they deliberately make this product for batteries. They were doing something else, and it generated this excess product that they're able to sell to people making batteries. And that's not the way to scale your supply chain for batteries, because they would have to scale that other business, and they're not going to be scaling that other business to generate all that material. So you have to think, okay, how are we going to make electrolytes? And when our focus is making electrolytes, how are we going to make graphite when our focus is making graphite?
There hasn't been a lot of like dedicated investment in specific battery materials and refining processes. And that is changing, which is great. It's a big opportunity for a lot of different players to dedicate their mental efforts towards something that is needed to achieve this scaling.
If you start making electrolytes deliberately, or you start making graphite deliberately, or other battery components deliberately, you probably end up making that part of your supply chain more efficiently than when it's an offshoot of something else. You probably find a way to manufacture the electrolytes, the graphite, whatever it is. You find a way to generate that material in much higher volumes, much more efficiently than how it's done now. So that's a big benefit.
Specific to battery making, like the cathode synthesis, or how electrodes are made, or cells are assembled and battery packs are made. Sure, there's been bespoke investment. It's a bunch of unique stuff. But even that is not scalable like it needs to be to go to the huge multiple we're talking about.
They're trying to scale battery production much greater, and a couple of battery factories here or there doesn't get it. We need to come up with a model for manufacturing batteries in massive scale. And I think Tesla has taken steps in that direction with 4680, but more needs to be done, and that's something that Tesla is working on. And that's something others need to work on. We need the industry to scale. We need a much higher volume of battery production. Next, Drew makes an interesting analogy in talking about how to build your next battery factory. He compares it to building your next bread factory. You start off small and you're going to build a bigger bread factory. So listen to this. And there's an intro from the Stanford professor first.
This scaling, just being, as you mentioned, pragmatic and scaling up, but also constantly looking out for ways to improve. Can you maybe comment on a couple of exciting directions you're thinking, how you can change the next set of factories you build?
Yeah.
Mining processes.
Sure. I mean, I think the kinds of stuff that we've been focused on within the scope that we've taken on to date, which has been kind of like cathode and up, you know, we've really been thinking about the typical things that you think about when you're making bread. Like the last bread factory could do 1,000 loaves an hour. I want the next bread factory to do 5,000 loaves an hour. Like, what do I do? Do I like change the chemistry and like a little bit more baking soda, a little bit more magic pixie dust, and it just rises faster? Or do I get a bigger oven? Or, you know, is my mixing going from like 1,000 liters to 10,000 liters? Is that how I make 5,000 loaves versus 1,000? You know, that's kind of like things manufacturing engineers have done for a while, and we're doing that with, you know, the bigger form factor cell and the more efficient assembly lines and the slightly different electrode processing that we're doing. That's all about how do I make that same factory do 5,000 loaves an hour, same footprint or smaller, do 5 times to 10 times more than it did before. But that isn't the fundamental bottleneck of the next 10 to 20 years.
First of all, he dives into this idea that when you're trying to think about your next generation factory, you got to think, okay, I have to do something significantly different if I want to get the next generation factory to produce much higher volume in maybe even less amount of space. That's something we see with Giga Texas, was like a revision in how we built things. And we're going to see with the robotaxi factories coming in 2023 and 2024 is how do we take what we've learned from building our first factory to build our second factory? How do we take what we've learned from building our second factories or our second generation of factories to building the third generation of factories? And then we're going to get into what the real bottleneck is. And he talks about this a lot. This is where it gets tight.
This risk area at the moment, again, I mentioned lithium like 3 times already, is really lithium. So how can academia help? There's tons of ways, like better ways to do direct lithium extraction out of brines, out of various different types of ways in which lithium ends up in water, like in the salars and other things like that. More extensible resins for things like ion exchange membranes for getting lithium purified. I mentioned it, I'll mention it again, like oil-filled lithium, there's a ton of lithium in oils. There's lots of ways to like rethink the lithium problem and remove fossil fuel inputs into the lithium refining process, find ways to actually sequester CO2 in the lithium extraction process. There's tons of stuff that's exciting, but not yet fully there.
It's all about the lithium, folks. There's more here. We're going to talk about some other things, but lithium is huge. Drew is obsessed with lithium. We need to get more lithium. We need to get more lithium. We need to get more lithium. If you're going to do 15 to 20 terawatt hours of lithium ion batteries a year, you're going to need a lot of lithium. There's an interesting solution coming up next about what we can do if we don't do enough lithium. So check this out.
Why lithium? Why not something else, like maybe sodium? And there's a lot of work going on with sodium in academia and in the startup world, where if it were possible to get sodium to be as compelling as lithium is, especially for grid storage, where energy density doesn't really matter. It's more about, the life cycle of energy.
Energy density doesn't matter for grid storage because you can make grid storage large. In a car, energy density matters because the weight of the battery pack matters a lot, and the volume that the battery pack takes up matters a lot because it can interfere with the operation of the car. If the battery pack's too heavy, the car doesn't drive well. If the battery pack takes up too much volume, then it's too big to fit in the car. Or you can't fit as much battery into the car, you don't get as much range. But with energy storage, you just take a big piece of land and you put larger megapacks out there, and maybe the megapacks are twice as large, doesn't really matter a whole lot. They don't take up a lot of space compared to what you need. Can there be a sodium-based solution that saves the need for all that lithium?
Maybe we do sodium for the grid, which like greatly reduces the need to scale lithium. These are the kinds of things that partnership between academia and industry can enable this 50% year-on-year growth of energy storage for all the ways in which energy storage can, decarbonize the grid and transport happen sooner. Happen more facilely, I guess. Like ultimately, the current road of like lithium or bust is possible, very possible. There's plenty of lithium. It just would be great if there was just like one more entree at the table. So sodium might help, and other things like that might help.
I believe the word he used there was facilely or more easily. Sodium could be a big answer. It was interesting he talked about this. Remember, he's at a university. Tesla is a company. It's industry. The university is academia. This idea of academic industry partnerships. Is there research, and this is going to come up again in this video, is there research or angles that academia can take that can help industry succeed in delivering the transition to sustainable energy, sustainable transportation, the electrification of the grid, the electrification of transport? How can academia participate in that? How can academia make a difference in this? That's a little bit of a part of what this conference is about. Now, there's an interesting bit here about peak oil. Peak oil is a concept that was talked about a while back, that we were going to run out of oil. And when were we going to reach the maximum amount of oil we could extract? And listen to how Drew talks about that.
I remember before this building was built, going to all of these, talks about, when's peak oil? When's peak oil? Is it 2009? Is it 2020? Is it 2030? Is it never? And I think it seems likely that peak oil is sort of near now, not because we're going to run out of oil, which didn't end up being correct, but because there's just a better alternative. And that's eventually going to be true of gas too. Not because we're going to run out of gas, but because we're going to decide, hey, maybe we should use gas for really useful things that only gas can be used for, instead of heating people's homes and other things and businesses and industry and industrial processes. So it definitely is a very exciting time for that reason.
For a long time, there was talk about at some point we're going to run out of oil. And Elon talks about how, hey, for sustainable energy, at some point we're going to run out of oil, we're going to run out of fossil fuels, so we need to shift to sustainable energy at some point. And Drew's point is we're actually going to hit peak oil not because we're going to run out of oil, but we're going to reduce the demand for oil. We're going to reduce the demand for natural gas. We're going to reduce the demand for coal by switching to solar, wind, battery storage, electric vehicles. All of these things are going to reduce the demand for fossil fuels. So the demand side will cause peak oil, cause the demand for oil will peak, and the usage of oil and fossil fuels will decline because of the demand side rather than the supply side. It's an interesting take on things. There is plenty of oil, there is plenty of gas, there is plenty of coal in the ground that could be extracted, but it would be better if we didn't extract it or we extracted less of it, and that's where we're heading. Now, this is where Drew gets to a point about the challenge of mining, or one of the big challenges in mining, getting enough materials out to be able to manage your supply chain for the battery industry. Check this out.
The public psyche about electrifying everything and like solving the climate crisis and electric can be better is coming around. Now, there's still a lot more to do, especially in the building space, to like facilitize the electrifying of everything. In the utility space, especially with rules and the various regulatory structures to like enable the full capability of storage of any kind. It doesn't matter whether it's a concrete in an oil well or air in a cavern or lithium-ion battery intercalating between a cathode and an anode. Like, none of those storage mechanisms are really being fully tapped with the current regulatory structures. So there's more to do, but there's a ton of momentum, which is exciting.
Next, we're going to hear Drew talk about cathode. Cathode is one of the essential details in Tesla batteries, in lithium-ion batteries generally. Are you using nickel? Are you using manganese? Are you using nickel, manganese, cobalt? Are you using iron batteries or iron phosphate batteries? A lot of different options here. Listen to Drew talking about cathodes.
The other thing is, and maybe you've heard people talking about Tesla using something other than just nickel. Like, for sure, we're like equal opportunity cathode company. Like, whatever, seriously, whatever can be, sensibly mined and refined without undue environmental damage or social destruction, and is like reasonably available, and we're not doing crazy things in crazy places. Like, we're willing to entertain using, but it would be fantastic if we could get rid of the metal in the cathode. And there's some research efforts that are out there also.
Get rid of metal in the cathode. Let's see some interesting research.
Do kind of like graphite on graphite or other sort of non-transition metal cathodes, which would be fantastic. I encourage all of you, if you are an electrochemist or fancy yourself to be one day, to take that on, because finding a way to avoid having to mine and refine 300 to 500 terawatt hours worth of transition metals would be fantastic.
In other words, right now the plan is to mine and refine transition metals, which is nickel, manganese, cobalt, iron. There's these metals that are used to basically store the lithium or discharge the lithium as the battery charges and discharges. And if we could find another way to make batteries that didn't require those metals, it might be a much more cost-effective way, and it might be a much easier way to scale batteries to enable the future of grid storage and of vehicles running on battery electric instead of other alternatives. Accelerating the transition to sustainable energy, sustainable transportation, maybe some other kind of cathode other than transition metals would make a difference. Pretty interesting, but there's more here.
And then you wouldn't need to go through the pain of, not that it's impossible, of recycling that either. I mean, you would still recycle that, but you wouldn't be having to go through these crazy synthesis steps that are part of these transmission metal cathodes today. Crazy is a strong word. It's doable. It's just, you wish you didn't have to.
We're going to talk more about recycling later in this video, but this idea that if we used a different material, that the challenge of recycling would be a lot less important. There's hassles with recycling. We're going to talk about recycling next. So recycling the transition metals. In other words, when the battery's done with its life, they bring it back and they extract the minerals that are in the battery. They extract the nickel, they extract the manganese, they extract the cobalt. This is a more efficient way of getting those materials than digging it up from the ground, but it's still not that efficient compared to if we can come up with another type of battery technology that doesn't need these metals at all. Next up, Drew talks about recycling.
We think about recycling or repurposing, we think of it as a generally a understood process, just has to be scaled.
Yeah.
Could you comment a bit on what's the missing innovations that we can still pursue?
Recycling is the end game for sure. So we get the 300 to 500 terawatt hours built. We get, let's say, 90 to 95% recycling efficacy. That means only 5 to 10% virgin material. And recycling, just as a total embedded energy and embedded cost way to get these resources is like an order of magnitude-ish lower cost and lower embodied energy. So it's a huge and obvious end game.
It is much more efficient to recycle battery materials from existing batteries than it is to dig up those materials from the ground and refine them and bring them to the factory. It's much more efficient, so they want to recycle whenever they can. The reason this hasn't come up in the video, I don't think, the reason why recycling doesn't matter that much yet is there aren't enough batteries in use yet that are coming out of use even. There aren't really enough batteries yet that are in use. When a battery reaches the end of its life, when a Tesla, let's say, has 10, 15 years on it and the battery's no longer that good and you want to take that out, there just aren't enough electric vehicle batteries out there. And the size of an electric vehicle battery is so much larger than a phone battery that, taking a bunch of phone batteries and recycling them is nice, but you're just not going to generate a lot of battery materials from that. As we scale production of vehicles, we get to 20 million vehicles a year from, let's say Tesla. 10 years later, those vehicles will be coming in for recycling, but it's going to be 10 years later. So recycling matters a lot more 10 plus years from now than it matters right now. But it's important to start figuring out how to do it well now so you're ready when the time comes.
We're doing recycling up in Reno at the Gigafactory, and we've got our approach to it. I think that the areas where we're still developing and where there's still more opportunities, it actually is similar to what we just discussed. Like, how do we get lithium out of water or like solutions more easily? But there's a couple other areas where it's kind of I don't want to say mundane, but it's like maybe not historically considered like super sexy area, but just like water treatment in general. Because if you think about different ways to go after the recycling problem, there's the way of like burn it all, and even if you burn it in like a low oxygen environment or whatever, like you're still burning it, which has its own like air side treatment challenges, or you're doing it with water and then you have water side treatment challenges. Either way, there's like kind of the nasties that you need to deal with. And there's more research required to sort of downsize the capital cost, improve the efficiency of those solutions. Some of them have a lot of overlap with the hydrogen, like the new hydrogen wave of like, how do we get hydrogen produced, which is like, how do we make electrolyzers cheaper? That's also in battery recycling as well. So there's a lot of overlap between kind of areas of the new economy that help each other. So yeah, electrolysis, water treatment, which tends to also include electrolysis, as ways to kind of get back out the pure materials that you need to start the process again.
Use nickel, manganese, cobalt, iron, whatever to create your battery. When it's done with its life cycle, you want to extract that material out. And there's issues with water treatment. There's issues with, are you affecting the air? And again, this is sort of like, how can academia work with industry? Can people in academia figure out ways of solving some of these problems? That's one of the focuses of this get-together, this conference. Supply chain is a huge topic that's playing a big role in what's happening with batteries and everything else in manufacturing. Drew talks quite a bit about the global supply chain and trying to establish local supply chain. Listen to this.
What are the challenges, problem Tesla is facing? How do you guys address that in terms of global supply chain or thinking?
Yeah, I mean, wouldn't it be great if we could all just get along? I mean, yeah, there are plenty of difficulties. associated with COVID, associated with policies that, you know, former administrations, future administrations are putting in place, that do serve to kind of like, it's like kind of an undue burden on this, I think, like pretty existential threat need to accelerate the electrify everything movement.
Now, this was a little bit of a, Drew's trying to be really careful here because this sounded like a political shot at governments. I don't think he's speaking specifically about the U.S. government necessarily. Obviously, Elon hasn't been happy with the Biden administration. I think this is just generally a global problem of government. They say they care about climate change, but when it comes to, hey, if we're going to shift to electrification, if we're going to accelerate the transition to sustainable energy and sustainable transportation, we need to clear up these supply chain issues so we can get the stuff we need so we can make the things that will resolve these concerns and resolve your concerns about climate change. The politicians say they care about climate change, and when industry comes to them and says, hey, we can do something about climate change, but we need to free up this issue in the supply chain, they don't really get the response that they need from government because government is not really, they say they care about climate change, but when push comes to shove, they care about special interests a lot more than they care about climate change.
It is frustrating, but like all we can do is sort of our best to work around it. Ultimately, it does make sense for there to be a local supply chain for energy storage on every continent. And, you know, similar to every other new economy thing, China has very well does a fantastic job of like investing in what is necessary to get the job done, whether it's solar or batteries or otherwise.
One of the things that I frequently hear in conversation and talk with people about, there's all these people who are upset about China one way or the other. Americans think China is the enemy. And look, the practical reality is if you think climate change is a problem, China's doing a lot about it. China is establishing their own, they've set up incentives, they've built their own supply chain, they've become the supply chain for the world because the government has encouraged investment in those areas and our governments haven't. The United States government, European governments, other governments. Drew is saying we need to make those investments here, we need to make those investments in Europe so we can have a supply chain everywhere. But I will often hear people critical of China, and it's like, well, wait a minute. China's just doing a better job than our governments. You can dislike the Chinese government all you want, and I don't like any government. But right now, it definitely looks like the Chinese government, when it comes to issues like this, electric vehicles and more, and manufacturing generally, China's just doing a better job. And that's because our governments aren't that good. And Drew is a lot more polite about it. Elon's not as polite about it as Drew is here. I'm a lot less polite about it than either of them.
And the rest of the world lets them do it. And you know, the industry around that sees that happening and sort of like follows the capital, and then you get what you get. There's no reason why China is the only place that battery materials are largely refined and synthesized today. Like, there's not a good reason, right? It just is where the capital has gone because of government intervention. You know, American manufacturing, European manufacturing, Asia, you know, Australia, it doesn't matter. Like, everybody can do this stuff. This isn't like nuclear technology that's held in lock and key and governed by a treaty. So everybody should be doing it, and I think with the general awareness again in the public psyche that this is coming, I expect more and more policymakers to be intentionally attracting local capital to do the mining, refining, the battery making locally, which I'm 100% supportive of. And Tesla has been doing it. I mean, we're putting money where our mouth is. Huge 100 gigawatt hour battery in Texas, factory in Texas with Cathode there. Same thing in Berlin. Like we're in recycling in both of those places. Like we're doing what we can do. Everybody is excited to do that, I think.
Tesla is working on localizing their supply chain in terms of making the batteries where they make the cars. And I believe one of the things you want to watch for is who's building 4680 cell factories, where are they building them? That's where you might see a Tesla Gigafactory. And I think more important, you need to go further up the supply chain. What are the supplies you need to make batteries? So where are you getting your nickel from? Where are you getting your manganese from? Where are you getting your cobalt from? Where are you getting your iron and phosphate from? And lithium. Where are you getting these raw materials so that you can make the batteries you need to make? These are additional challenges we're going to see in the future. And Tesla, I'm confident, is working on them, trying to go upstream, get the mining and refining. You want to mine the materials, you want to refine the materials, you want to do that closer to your factory. Elon, at one point, talked about you want to minimize the distance you move all these molecules. We're moving molecules all over the world so many different times. Can we localize so we dig up the molecules, refine the molecules, and put them in the factories to make the products all close to each other so you don't have to move everything all over the place. I think that's coming. It's going to take some time, but I think Tesla's definitely working on that. So I'm skipping around in this video a little bit because I was just talking about mining and refining, and there was a question that related to mining and refining and Drew's answer. So let's address that first, and then we're going to go back to the million-mile battery and battery life.
Talk about the 3 terawatt we have to build, right? I think that's kind of like
300.
Right, 300, right?
Yeah.
And now we're kind of getting into like a planned economy, right? We know how much we're going to get there. Yeah. So, and we also know how much we want to build in the United States, right? So I want to ask actually a question regarding to the business side, right? What do you think is actually the things that prevent you from building factories, getting these things done? What are the critical things you think if we can change the policy that, there will be more and more factories being built quickly? So.
Yeah, the factories are not the issue at the moment, honestly. Like the permitting and construction timeline of a battery factory or a cathode factory that does the cathode synthesis, or even like the anode finishing stuff for the anode, it's maybe 2.5 years from like beginning the process to ending the process and ramping production. You could do it a little bit faster, it might take you a little bit longer, but that's really not the bottleneck on the 50% year-on-year growth. It's the fact that, there's enough lithium in Nevada to produce enough batteries for all of the vehicles in the United States. But the last mine to come online in Nevada took 10 years to get permitted. That is the bigger issue.
It's easier to build a factory. It's harder to get a mine. It's like manufacturing is easy, mining is hard. I'm going to play on Elon's prototypes are easy, manufacturing is hard. So the governmental rules delay mining and then maybe also refining, and that makes that part of the process slow. And that's one of the things that's a challenge to scaling up production of batteries and changing the world in the way that Tesla and we want to change the world.
It is that issue. It is the resource extraction timelines in most of the developed world, and most of the developing world now too, are just extended for some good reasons and some not so great reasons. And that's where kind of like the direct hand of government could help improve that, and it's not like there should be no environmental process. That's not what I'm saying. It's just we need to find a way to not have like 3 in a row, which is typically kind of how it works, where it's like you do one and then like it's reevaluated again by another group and then another group, and then like every step along the way there's many opportunities for public comment and lots of thousands and thousands of pages to write. So that's the area where it's not the factories. The factories are easy. It's the mining and refining that is slow.
Factories are easy, mining and refining is slow. One of the things, I'm very critical of government, just in general, critical of government. And one of the things is you will hear all these politicians say that climate change is an existential threat. And here's a company that is trying to do something about climate change. And then other environmental issues, which are legitimate, slow the process. And the way governments have set up the process of addressing these environmental issues makes it take longer than it should. And that makes it harder to achieve the goals we have for avoiding climate change, avoiding CO2 emissions, avoiding other pollution. If we want to shift to electric vehicles, if we want to shift to electrify the grid, then at some point, the environmentalists who came up with these other processes have to say, hey, wait a minute, what's more important to you? This process that protects some local environmental issue, or fixing global climate change, which you keep telling me is going to destroy humanity and destroy the earth. And one of the things I personally find with environmentalists is they don't believe that they have to make choices. They think everything is bad. Humans are bad. They would be happy for humanity to go extinct and the planet would go on. That's ultimately what I find. I get very critical about the environmental movement, the radical left, the Democrats. They say they care about something, but when push comes to shove, they care about this is the way we've done things before. These are the special interests we have to protect. This is the process we have to follow. We saw this with Giga Berlin and the German government slowing Giga Berlin from being built. Get out of the way. This is something that's clearly good for the environment. Let's make it so that these environmental reviews happen quicker. Make them good, but don't make them take so long so we can get the mining done, so we can get the lithium out of the ground, so we can refine the lithium, so we can put it in batteries, so we can fix these problems. Okay, next up, and I thought this was really fascinating, this question of the million-mile battery, or this guy right here is the questioner. He's asking about a battery that can last for 100 years. And Drew has I find a pretty interesting response to battery life. He kind of poo-poos Jeff Dahn's million-mile battery concept, but there's a lot of depth here. This is one of those moments where Drew shows tremendous depth on a topic we know he knows about. This is about batteries, and this is Drew's wheelhouse. But the depth that he shows on batteries is really, really interesting here. This is really good stuff. Listen up.
My question for you is, what do you think are the main scientific challenges to arrest aging of batteries? So if your battery can last 100 years, what would it take to understand aging, reverse it, arrest it? Is that something you're investing in?
Yeah. So the interesting thing about that question is that there's like this belief that people can make things that last forever. But when was the last time you looked at a house built in 1950 and said, everything in this house looks amazing?
This was funny because the response didn't really go the way Drew thought it was going to go. He was trying to make a point, and the guy distracted from it and lost the point, but hopefully Drew gets it back.
Right? Like
well, I grew up in Jordan, and we have houses that are 300 years old. So,
okay.
so I'm not sure that holds.
Okay. Counterpoint,
Yeah.
argument. I understood. I think if we tried to make that same 300-year-old house in Jordan today, it would probably cost a little bit more.
A lot more. Yeah.
And that's kind of the point, I think, is, we need to get to the point where everything lasts a similar amount of time. And, the financial engineers that started making solar affordable kind of bet on the come that solar fields would be deployed and last 20 to 30 years. And they were kind of wrong. Because even though in the lab everything looked great, when it got out there were a lot of failure modes that they didn't understand.
In the lab, it looked great. When it got out there in the real world, there were failure modes they didn't understand. What Jeff Dahn talks about with batteries in the lab isn't the reality of what's going to happen with vehicles on the road. Interesting point. Drew, keep going.
But eventually, with improvements in backsheet and sealant and all these other things that have happened over the years, they kind of last 20 to 30 years. Batteries, we can look at them electrochemically, and we can, Jeff Dahn says 1 million miles and stuff. Yeah, sure. You can do all of that, but that's just in a controlled lab environment, the intercalation reaction, of like lithium shuttling back and forth across separator. It's not, does the battery system around those like nanometer scale things hold up for 20 to 30 years?
Yeah, but that's maybe where simulation can help.
Yeah, absolutely. And these are the things that we need to figure out. It's like, how do you maintain, perfect sealing? You can't get any water inside the batteries, or they're basically done. So how do you maintain that over 30 years? You need to maintain the head pressure. Like you need to manage the gassing that happens in at least liquid electrolyte systems within the pressure capability of the device. You need to manage the sort of like volume swell and everything else of the various materials involved through the lithiation and delithiation, so that you don't end up with any sort of material moving out of the way in funny ways to result in weak shorts over time.
It's just interesting here, Drew gets into, there's so many different things that can go wrong with a battery aside from the battery chemistry itself. And that's one of the challenges that Tesla faces and that all these manufacturers faces. If you want your battery to last longer, it's important. One of these, he referenced 20 to 30 years, and I don't think the life expectancy of a robotaxi Tesla needs to be 20 to 30 years. If it's going to drive 100,000 miles a year, it's going to have a 1 million mile battery, then 10 years is enough. So it's not clear how much of this durability relates to just time and how much of it relates to miles driven and the wear and tear of the miles driven, as opposed to the wear and tear caused by time itself.
These are very hard things to simulate. There is work going on at Tesla, Vinit's in the back, trying to simulate a lot of this, and we're getting better. But we're definitely not at the point where I can confidently tell you that the battery installation, for all that we know about it, is going to last as long as the solar installation. And by the way, it took them at least 40 years to be right about their predictions on the solar side. They were wrong for 20 years in saying it would last 30 years before they finally got it to sort of last 25 to 30 years. So we'll get there. And it needs to be done so that the same way that you deploy the renewable energy capital, you deploy the storage capital on the same financial engineering spreadsheet, and it's all on the same sort of replenishment timeframe. That's where we need to get to for the grid storage side to be as low cost as it should be and can be.
So here you have this issue with, if your battery, let's say, lasted 100 years, but the car only lasted 20, what do you do with the battery? And then even if your battery does last longer or you have a use for that battery, the new batteries that are going to be available in 20 years are going to be so much better than the battery you built 20 years earlier that the value of that battery may not be as great as you think. There isn't necessarily that much advantage to have a battery last 100 years. That's, I think, the key point. You want the battery to last as long as the solar panels. You want the battery to last as long as the car. You don't necessarily need the battery to last longer than the car or longer than the solar panels. It's an interesting point. But wait, there's more about battery life from Drew Baglino. Here we go.
When you came out with the Roadster and the Model S, you probably had some internal predictions on when the battery would fail. And now you have the data.
Yeah.
How was your prediction at that time? Because you knew a lot less back then.
Yeah, we were very pessimistic. we were unnecessarily pessimistic about how long the batteries would last. Electrochemically, we were over optimistic on how long they would last for all the other reasons. So we had water ingress issues at the battery pack level that had nothing to do with the cell that we had to learn about how to deal with. We had a lot of, there's a lot of electronics in batteries to monitor all the cell voltages and do all that stuff. And we had learnings about ways in which electronics can fail and maybe whether or not they should be serviceable so that that's not a reason to scrap a battery. We had some learnings about, shock and vibration or thermal cycling that don't show up until you've been in the field for 10 years that had nothing to do with the cells. So honestly, looking back on it, the cells have outlasted our expectation. Outside of the cell has come short of our expectation. Yeah. And that's something that as sort of the design world sort of solidifies over, it doesn't matter whether it's a prismatic or a pouch or a cylindrical cell, like the way that you package that into a battery pack, as that kind of lands on a consistent structure, similar to what's happened with solar. Like if you look at a module today, you look at a module 20 years ago, it's very similar, basically the same construction. Those failure modes will be understood, and we'll be back to the electrochemistry being the dominant thing we need to do a better job understanding. We're not there right now, which is interesting. It's not what you'd think. It'd be like if the engine person was always asked, well, what about your piston seals? And the engine person was like, actually, it's always the exhaust system that fails first, which is kind of true.
This is just a key point. A lot of us who are into the battery stuff, my favorite channel on YouTube is The Limiting Factor, and we talk a lot about battery chemistry and how that relates to battery life, the million-mile battery, that sort of thing. And Drew is pretty much saying, hey, electrochemistry isn't the real issue. It's other things in the battery pack that fail based on wear and tear, mileage, years, weather, water intrusion. There's all kinds of things that go on. So at some point in the future, battery chemistry will matter for battery life, but right now, so many other things in the battery pack are still challenges. And obviously, they've learned a lot in the last 10, 15 years, and they're going to make progress. They've already made progress. They're going to make more progress. But our obsession with battery life, the length of time or the number of miles that the battery will serve, turns out we've probably been wrong all along, and there's these other manufacturing issues and construction issues and protecting the battery issues that are just bigger. Okay, next up, this is off a little bit the energy storage topic. The gentleman you can see in the lower left corner of the screen asked a question about Solar Roof. Drew dives into Solar Roof. Very interesting response. Drew is not responsible for Solar Roof or solar panels, but one of the things I noticed, even though it's not his thing, he seems to know a lot about it, and he has Solar Roof on his house. Listen to Drew talk about this. Listen to the question first, and listen to Drew talk about this.
Just like it's taken decades to develop solar panels that we get good performance, it's also taken decades to develop the solar shingle that combines a solar panel and roofing materials.
Yeah.
I was involved in the 90s, used to carry one around in my briefcase. You guys finally figured it out. I have a set on my house, and they're quite amazing. But I'm wondering how committed you are to that technology. Can you drive costs down? There's a very ugly story in the New York Times about Tesla and the solar shingle, and I'm really hoping you stick with it and turn this into a real product. 6 million roofs get replaced every year in the United States.
Yeah.
And if you really want to make solar roofing happen, it's not solar panels on a roof, it's the roof is both roofing material and solar.
Of course, the media took some shot at Tesla over Solar Roof. I don't remember seeing the article. I'm not sure which article he's talking about. But the New York Times, one of the inspirations for my other channel, The Daily Lie, is the New York Times, the paper of record, right? I think the media lies to us constantly. So, of course, the New York Times took some kind of shot at Tesla Solar Roof. They always taken shots at Tesla and Elon. The company that is making the world a better place, the guy who is leading this, and just some guy at Stanford at this conference mentions the New York Times. He didn't blame the New York Times for it. I do. But anyway, listen to Drew's response.
Preaching to the choir with me. I mean, Lacey, my wife, was in the car with me earlier today, and I was like, that should be a solar roof, that should be a solar roof, that should be a solar roof. Look at that, like, 50-year-old wood shake roof. It's a fire hazard. That should be a solar roof. So, yeah, I mean, we have a solar roof on our house. I think.
So Drew is a true believer in Solar Roof, right? The comment you're going to hear in this that he doesn't even lead the team. That's not his. They don't report to him. And if you don't realize this, there's Tesla's 3 key people on the website. There's Elon, there's Drew, and there's Zach Kirkhorn. So I'm not sure who's in charge of Solar Roof. I'm guessing that person reports directly to Elon. Drew is sort of, chief technology officer. He's the lead engineer in the company besides Elon. And he's not responsible for it, but just listen to the depth of his knowledge about Solar Roof and solar in general. It's just amazing.
I think the thing that Tesla, I mean, it's kind of like a common ivory towerism kind of problem. Like, if you sit in a closed environment and imagine an ideal product for anything, you can like optimize the stuff that you do at the and like completely miss the forest for the trees and the stuff that you don't do. And so with Solar Roof, we spent a lot of time on the shingle and not enough time on like the stuff around the shingle. When I say the stuff around the shingle, like there's a lot of perimeter flashings on a roof, a ton of perimeter flashings on a roof. You take a 2,000 square foot roof, there's like, I don't know, 8,000 linear feet or something like that of flashing stuff. And that doesn't even include any of the obstructions and stuff like that.
One of the challenges Tesla has with Solar Roof that they figured out as they started deploying Solar Roof is, and I experienced this, I had a Solar Roof order for my house, and one of the things they figured out is some roofs are more complex than others. So some roofs are just roofs. A lot of roofs have holes in them for exhaust vents or other things. And one of the reasons, my initial quote for my roof ended up being massively increased, and one of the reasons was there are all these protrusions in the roof and you have to work around them when you're doing your roofing. So making the tile good is great, but you've got to make the roof system work, and you've got to make your tile work with the roof system. And it turns out that's a lot harder than they realize. We've known this for a while now, but Drew's just sort of recounting that. Anyway, here's some more from Drew.
The engineering team spent a lot of time making that shingle awesome, and it's super easy to build and like not expensive at all, and not enough time working on making the roof job as simple as possible. And that's where the focus is now. I can't really comment because they're not responsible. I'm not responsible for the Solar Roof, and I'm not making the like product decisions. I can't really comment on how enduring is our commitment, but I can say that like personally, my vision is and Elon has stated it very many times, and you've all heard it, is that every roof should be a live roof, not a dead roof. Wouldn't that be great? Isn't that how it should be? And like the tile, the thing that we're making is not the reason why we can't do that right now. It is not an expensive roofing material, and it generates plenty of power for what it is. So it's everything else about it. And in the same way that asphalt shingle roofs didn't start out cheap, and now they are, like it'll happen.
One of the things that's notable to me, the question was how committed is Tesla to Solar Roof? And Drew is arguably the number 2 guy in the company, and he's committed to it. And Elon has repeatedly said he's committed to it. And he's the number 1 guy in the company. I don't know if Zach Kirkhorn has an opinion. He's tied with Drew for number 2. I don't know who else has that much influence in Tesla that they would take away from that. I think there's just this challenge of, can they get to the point where the roofing job itself is manageable? I love what Drew said, that the shingle itself is not an expensive roofing material. They've got the manufacturing. This is important. They've got the manufacturing of the solar roof shingle or solar roof tile down to a reasonable cost with a reasonably high solar productivity. So it's just an engineering challenge. How do we make this work on all the variety of roofs around? My personal take is, I believe they're working with some home builders to come up with a different way of doing this so that they build them on homes rather than new homes. Long run, you want to do it on existing homes because, like the guy said at the beginning of the question, 6 million homes a year get solar roof replacements. So I would love to see that happen, but there's so many new homes built, and there's plenty of opportunity for Tesla to scale solar roof on new homes first, if they can swing that. And then you can design the roof for solar tile, for solar shingle, instead of trying to make the solar shingle work on existing roofs. So maybe they get that done first. And I've heard that they may be working with some new home builders, that may be coming first. Because if you can do that, then you can move the protrusions to the side of the house instead of in the roof of the house. That makes it a lot easier. If you can make the roof less complicated, like a simple, pyramid-shaped roof or V-shaped roof, essentially, is simple. That roof on our house is so complex. There's so many different. When you make a house fancier for rich people, they end up making the roof very complicated. It's just the way it is. And simple roofs are easier to build, and simple roofs are easier to build for solar roofs. So we'll see what happens with that. I think it's very likely we will see solar roof continue when you have this kind of commitment from Drew, and we know we have this commitment from Elon as well. So we're almost to the end. Next is a question about battery swap. This is something I made a video about on my channel about battery swap because Neo Motors is relying on battery swap. And great question about battery swap. Great answer from Drew. Check this out.
Tesla is an industry leader to develop the fast charge. So the battery charging time can be shortened a lot. But to my best knowledge, I don't think Tesla is very actively looking for battery swap, right? Yeah. So may I know why is that? Can you help me to understand it?
We sort of looked at kind of like if you imagine charging as a standalone business, like with profit and loss lines and OpEx and CapEx to make it go, that's what we evaluated when evaluating like swaps versus charging infrastructure. And kind of like when you have the swaps, you still need the charging infrastructure, but now you need the swapping infrastructure too, and the storage infrastructure for the swap batteries, and all of the like mechanisms to do those two other things. So it's just on a pure P&L basis to like provide the same function to people didn't seem to make sense. And I'm responsible for Tesla Supercharging actually.
You notice he said he wasn't responsible for solar roofs, so now we know Drew is responsible for the Supercharger network. So I just thought that was an interesting little tidbit. We learned a little bit more about the structure inside Tesla. We're learning, what Drew is responsible, what Drew isn't responsible for. This is something I don't think we knew publicly before. Drew is responsible for the Supercharging network, and he's not responsible for solar roofs. So there's this interesting question: who is the number one person on solar roof? And who do they report to? Because they don't report to Drew. They probably report to Elon. So we'll see where that goes. But anyway, more about this profit and loss thing. But listen to Drew.
And we run it like a business, and it has its own P&L, and it needs to be profitable in its own right. And we look at all the costs, and you want to do the absolute bare minimum at the site to make the charging possible. And swapping is not the absolute bare minimum really at all. And if you look at some of our videos, like the pinned tweet on Tesla charging.
That tweet is no longer the pinned tweet on Tesla charging. It's a tweet showing the installation of superchargers at a location in Florida.
If you look at the pinned tweet on Tesla charging, there's a video of us building a supercharging station, like I don't know how many stall site in Florida. It's like 4 days of work, and it's all wired up, and The last 4 days are like landscaping to make it look nice. That is what you can do with charging that you can't do with swapping. It's never going to be like that.
The CapEx of swap is much higher. The amount of capital you have to invest to set up your battery swap station is dramatically higher than the capital expenditure of setting up a supercharging station. And rough numbers, if you can really do battery swap, let's say in 5 minutes from the vehicle coming in, getting the swap and going out, and the next vehicle going in, you know, that time from first vehicle into second vehicle in, if you can get each swap done in 5 minutes, that means a swap station can handle 12 vehicles an hour, right? So, and keep in mind, the idea that you're going to pull in and you're going to get swapped in 5 minutes ignores how long you're waiting in line to get your swap done. So in that same time, if the average supercharger is used for about 20 minutes, that means 4 superchargers can handle the same volume as one swap station. And maybe its average is 30 minutes, and so 6 superchargers. The cost of deploying 6 superchargers is so much less than the cost of deploying a swap station. And the maintenance in superchargers is dramatically less than the maintenance of a swap station. There's so much more going on in a swap station. So the cost of operating it, and then there's another thing that Drew didn't talk about is you have to have batteries at the swap station. Those batteries, the extra batteries, right? Those batteries aren't in cars. If you're battery limited, if you're using batteries for your swap network, those are batteries you're not using in cars, right? You're limiting the number of cars you can produce because you don't have enough batteries for your cars because you've got batteries stuck in the swap station. There's a whole host of problems with swap. And I love that Drew just pointed out, look, we couldn't make it profitable. We couldn't make swap profitable. We made superchargers profitable. All right, the last thing I'm going to talk about, the last clip here is for people who are academic nerds. Drew goes in depth about how academia can help, a particular way that academia can help. He references FEA tools, finite element analysis tools. Take a listen to this.
Maybe comment and maybe lay out for us, what are some of the capabilities or questions that you think academia is uniquely positioned to address that even well-resourced companies like Tesla can't get to? Something that we can uniquely contribute.
Yeah. I was saying this to you earlier. So when you look at what Tesla or any other company is struggling with as we sort of go from R&D, which is like not academic R&D, but like industrial R&D, to scaling and production, it's a lot of interdisciplinary problem solving that pulls together mechanical, electrical, manufacturing, chemical, materials to solve, challenging problems. The people on my team say they probably work on 2 to 3 doctoral theses worth of work a year, but they're not particularly like headline grabbing problems. And that's okay. Like, people are excited to solve hard problems. They feel great when they solve them. But it's, like, this machine, the yield isn't what it should be. Why isn't it? Oh, okay, it's like because of the CTE mismatch of that and that over the temperature cycle of the process. It's wobbling it by a couple microns. And like, okay, I finally figured that all out. Now I know how to design it out through, like, these mechanical changes. That takes them, like, 3 months. But eventually they've solved that problem and the yield goes up by half a percentage point.
Half a percentage point. So you've got a machine that's producing batteries and the yield is 96%, let's say. And this extra work increases the yield to 96.5%. And that seems like such a small thing, but if you realize the volume of batteries they're producing, the value that's generated by increasing yield by half a percentage point, it sounds so small when you say it's just a half a percentage point. When you realize how much value that adds to the company, and with 3 months of work figuring it out, it's pretty amazing stuff.
Reflecting on the ways in which academia can help the industry, it's really about accelerating the pace of iteration. If we think about what enables products to get better over time, or technologies to reduce in costs over time, or capital costs to go down over time, it's an iteration loop every time. Like, we're going to try these things because we think it's going to make it better, or cheaper, or more efficient, or whatever. And maybe they do. It'll take us a year and a half to see if they do. And then if they do, it'll take us another year and a half to ramp them.
Think about that one little detail. A year and a half to test something out, and then a year and a half to ramp it. So there's a 3-year iteration cycle.
So it's like a 3-year full cycle in industry for something like a vehicle or energy storage system or something like that. How do we compress that time? I gave you an example of, finite element analysis is something that came out of academia as a way to accelerate the mechanical or electromechanical design of lots of things, stress members in vehicle chassis or rockets.
Little quick note here, working on the pod car engineering, I worked with a guy who was doing a design for me of the pod car, and one of the steps, actually two or three of the engineers, I think it was two of the engineers that I worked with, did finite element analysis of their chassis design as part of what they were submitting to me as potential pod car layouts. So finite element analysis is something that's real, that's used a lot.
Will the seatbelt, pretensioner yield under the crash event? Will the frontal crash zone crumple in such a way in a crash so that people in the seats don't end up injured? That's all come out of academic FEA. And in particular, like I was telling William, you before, like.
And just to be clear, academic means it's like in a university setting, they're doing research and they came up with this finite element analysis tool set that I don't think really existed in industry before, and now industry uses that academic development. So the question really is, what else can academia do? What else can they do in the university environment to create tools or do other things that would help Tesla and others accelerate the transition to sustainable energy and accomplish the missions that Tesla's going for, especially related to energy storage in this case?
Finite element analysis for motors has, like over the past 20 years, has done amazing things for making electric motors more efficient. And that is a tool set that is working through the fundamental equations of the materials, Maxwell's equations, the everything that's associated with electromagnetism, and allowing you to predict the motor performance before you've even built it to really well, like within 1%. Think about how enabling that is. It shrinks the first 1.5 years to like 3 months.
So that was key. You got a 3-year cycle, 1.5 years of development, 1.5 years of ramping, and you've just knocked that first 1.5 years to 3 months because of what happened, because of the ability of finite element analysis tools to shrink that first 1.5 years, to take 15 months and make it, or take 18 months and make it 3 months. It's a radical improvement in the ability of companies to innovate. Tesla takes full advantage of that, so they innovate faster than others. Not everybody innovates to the same degree of urgency that Tesla does.
How do we do that with batteries? It doesn't work like that for batteries, really at all. You can do some stuff with some electrode modeling if you know everything about the materials in the electrode before you start. Or if you've already built the electrode, then you can characterize it. But even that takes a long time, because if you're thinking about a new material that's never been synthesized before, and it actually matters whether it's synthesized at a gram or a kilogram or 1,000 kilogram scale, oh man, now I got to build a 1,000 kilogram scale factory to know what the battery is going to perform like? That's like another 1.5 year cycle. So figuring out how to apply that mindset of investment in analytical tools for the purpose of accelerating things like electrolyzers or batteries or anode and cathode materials will be huge if we can get those tools into the tool chain. Because 3 years versus 1.5 years is that much faster of an iteration loop and that much faster growth and reduction in cost and reduction in CapEx and energy and everything else.
The answer to the question was, if academia can come up with tools to enable battery engineers to model things better so that they can shorten the development time so that they can try out new battery materials or new battery designs, that cuts the iteration loop time and makes it easier to innovate faster. So that's it. That's the Drew Baglino at Stanford presentation. Really, really impressed. I am, as far as I'm concerned, the president of the Drew Baglino fan club. If you like this video, please tweet the video or share it on social media with the hashtag Baglino fan club. I just love this guy. I think he's a critical player at Tesla. I love when you see the leadership team at Tesla, when you get the opportunity to speak with somebody or listen to somebody from the Tesla leadership team, and you see the depth of their knowledge and the breadth of their knowledge, you realize there's a deep bench at Tesla. Elon's the face of it. Everybody knows Elon's key, but there's a lot of really great people working at Tesla. And if nothing, you take nothing else away from this video, there's a lot of nerdy, geeky stuff, whether it's on the business side or the engineering side, that I take away from this video. But if you take nothing else away from this video, recognize that there's a great team at Tesla. Elon's always thanking the Tesla team. The Tesla team is awesome. A lot of great people. I think they have it built into the company that as you rise in the company, you learn a lot more about a lot of things that the company's doing, and that enables that ability for the company to achieve in a variety of areas, because they can pull an engineer from another project and say, hey, you're pretty good at this, we need you on this. And at the management level, the management people understand what's going on all over the company. So if management resources are needed or high-level engineering resources are needed at a different spot, they can be brought in. And I think it's actually cross-company too, that SpaceX people sometimes know what's going on at Tesla. Tesla people are involved in what's going on at SpaceX. Boring Company, Neuralink. I think there's a lot of cross-pollination. And this makes companies in the Elon universe even more effective, even more amazing. I am so excited about everything to do with Boring Company, Neuralink, SpaceX, and Tesla. I hope you are too. As always, check out the t-shirts at elonbits.com. This is a great t-shirt for getting attention. Check out my other videos. Please support this channel on the Locals platform, the Daily Lie, or on Patreon, or as a YouTube channel member. And thank you so much for watching.